Okay, class, welcome to lecture 29, the last one, big finale. Today we're talking about homomorphisms. So just real quickly, last time there was a big error. So go check out the description for how I fixed the error. That's okay. There's no mistakes in math, just learning opportunities. So no big deal. Okay, so in any case, this is the big finale, last lecture of the class. So the last thing we're going to do is understand this very fancy word up here. And let's think of some motivation first. So next, what we want to do is we want to understand, again, we're going to be thinking about what it means for two things to be the same. But the two things we're talking about now, instead of just having two different sets, we want to think about when a set equipped with an operation and another set equipped with another operation are, in quotes, the same. Because of course, the boring way in which they're the same is if A and B are the exact same set, and the square and the star are the same exact operations. So let me just clarify what these things are. So those are just sets, and then last time we learned how these things can be equipped with operations, where an operation just takes two things in the set, turns it into one in some way. So we want to think about what does it mean for the totality of everything to be the same, meaning the set and the operation. What does it mean to be the same in that situation? Okay, so as usual, after motivation comes little mini examples that sort of hint at the idea. So let's think about two sets here. So here's A, it's just going to have two little elements in it, 0 and 1. That's it. And then I need an operation. So here it is. So I guess I'll call it plus because it's sort of like adding, but it's a little different than regular adding. So remember, an operation is a function that takes in two elements and spits out another element. So in this case, because I only have two elements, I can actually just define the function on all possible combinations. So that's what I'm going to do to say what this function does. So I'm going to take 0 plus 0, that's going to be 0. 0 plus 1 is going to be 1. 1 plus 0 is going to also be 1. But then the weird part is 1 plus 1 is going to go back to 0 instead of 2, because there is no 2 in this set, just 0 and 1. Okay, so now I have A, and I have an operation, which is called plus, but it works a little bit differently. Okay, so now let me work over here for a second. Let's think about another set. So B will be the set that'll also have just two things in it. So already, just as a reminder, because A and B are the same in terms of number of elements in the set, they will have two elements. We already think of them as the same as sets in this fancy way called isomorphic. Okay, but anyway, that's different, but very related. Okay, so now we need an operation. So this one I'm going to call square box. So it's got to take in two things from B and give me another thing in B. So what I'm going to do is I'm going to, again, because there's only two elements, I'm just going to say what all the combinations are. So if I do T square T, that's going to be T. If I do T square F, that's going to be F. And F squared T is going to be F as well. But then if I do F square F, that's going to be T. So then in a very specific way, but right now very vague, these are basically the same. And maybe you can already sort of picture what's going on here. So the idea is really like, if I just think about 0 as being the same as t, oops, why did I use a different color? And then I think about 1 as being f, then I think about plus as being this box, then everything sort of starts to look exactly the same. And that is the idea. These two really are the same thing because I can rename the elements, but not just because of that. That's what it would mean to be the same as two sets. But I can also rename the elements in such a way that the operations behave the same. And that's the big picture idea. Okay, so let's write that down. So in a way, a comma plus and b comma box are the same because, and you can check this out if you want, if I just rename, if I turn 0 into 1, sorry, 0 into t, turn 1 into f, then sort of on its own, plus will turn into the box operation because everything will be the same, because 0 plus 0 is getting turned into, well, that adds up to 0. But then when I turn all the zeros into t's, then the box did that already by definition. And the same thing will happen with all the other guys. But do these, if I turn the 1s into f's and the 0s into t's, then the box operation is again what turned ft into t. So that's the idea. So then the sets, if I do this renaming business, are exactly the same. So I turn 0 into t and 1 into f, then the sets are exactly the same, and the two operations do the same thing. Meaning, okay, after I've renamed it, so I turn all my t's into zeros, and or the other way, whatever way you want to think about it. Now, plus is really doing the exact same thing to those guys as it did to 0 and 1, getting the same result. Sorry, this should have been an F over here earlier. Okay. So this is what we want to think about. And we can think about this in a more fancy way because we've seen many things like this before. This is really just the idea behind this is just a function. It's just a function that turns the elements of A into the elements of B. Except it happens to do so in an extra nice way where now I can also just turn plus into box and I get the same exact results. So that's the big fancy idea here. So the function f from A to B defined by f of 0 equals t and f of 1 equals f, it has this super special property besides renaming elements, and it's this, which is very weird. So the idea is that, let me just say it like this first, actually. Property of that, plus turns into box. So the operation from A is automatically getting turned into the operation of box in this way, which I'm going to say precisely in a second. So this is because of what happens here. So the idea is that no matter what two elements I start with in A, so it could be 0, 1, or 1, 0, or 1, 1, or 0, 0, any four of those combinations, any one of those four combinations, will obey this very nice property, which is if I do the operation in A, so this guy, it's all living in A. If I do the operation in A, and then I send it over by plugging it into F, that's going to be exactly the same as if I plug them in individually. So these guys both live in B now. If I plug them in individually, and then I use, well, because they live in B, how do I put two things together in B? I got to use B's operation. So the idea is either way is the same thing. So this side is saying do your operation in A, then send over. Then this side is saying send over both, then do your operation in B. And we're saying that they're always equal, they're always the same. So what this is saying is that the operation in A and the operation in B are exactly the same for their own elements, basically. So you could do either way. You could send things over separately and then add them, or you could add them and then send them. And that's the same. And then the way you think about this intuitively is when this happens, you think of F as preserving the operation or the structure. Some people say the structure. The idea being it turns plus into box because this rule is obeyed. So it's always good to see a non-example to compare to. So let's do that next. Okay, so we're still going to use the same two sets just because they're nice and small. So, and this operation will be the same. But for B, we're going to do a different operation. So this operation is going to be called arrow. So it looks sort of funky because there's two arrows, but that's the left arrow is the name of the function. So what is it going to do? Well, I'm going to take true, arrow true. That's going to equal true. This might look very familiar. True arrow false is going to be false. False arrow false is going to be true. Oh, sorry, I skipped one. False arrow true is going to be true, and then false arrow false is also going to be true. So you can already sort of see and compare how it looks a little bit different than this one did. You can sort of just tell that like it's a little bit different because now if I rename 0 to true and 1 to false, there's sort of like one little issue right here that doesn't really match up. Everything else matches up okay, except that one. And so, yeah, that's the issue. But now let's see how that works with this idea that we came up with here. So let's do the same function. So we just send 0 to true. Sorry, I said true, but I meant T. Whoops, slipped what it actually was. And 1 is going to go to F. So using this same function, let's see what's happening. So if I, for example, if I do 1 plus 1, that lives in A. And then I send that over. Is that the same as if I send f of 1 over, send f of 1 over, and then I use the operation over there in B. So these guys all live in B. Let's see. So f of 1 plus 1. Well, what's 1 plus 1? 0 in this land. And what does 0 get sent to? It gets sent to true. Let's see if it's the same. Okay, well, what is this side? F of 1, that's false, implies false. Well, that is true. So they are the same in this case. But that's a coincidence because I accidentally switched my examples while writing my notes at the last second. So I picked the wrong example. Okay, so now I know which one to pick instead, sorry. So I want them to not be the same. So let's try the one that doesn't seem to match up. That's the more obvious choice. I don't know why I didn't do that before. So now let's see, let's look at this versus this, but same idea. So 0 plus 1, that's just 1. F of 1 goes to F, right? That's where we sent 1 by the function. But then on the right side, F of 0, that is true, T, and F of 1 is F. And that, by our definition of our operation, is T. So no, it doesn't match up. So the idea is here is that these two operations are not doing the same thing for the elements when you rename them. And you can sort of just see it right there, but this is how we actually show it. These are not the same. Okay, and in general, when this does happen for any two elements, then that's called a homomorphism. That's what the definition we're learning today is. But if it just happens sometimes, like here, it happened once, that's not good enough. It has to always happen. Didn't happen for those two. But the earlier example, it did happen always. Okay, so this is the big definition of the day. So if you have a set and an operation equipped on that set, so I need some fancy names. Let's see, a comma box to be very general, so I don't have specific ones in mind, and another set with an operation. I'll call this one like star, something. Then a function from A to B is called a homomorphism. The fanciest word in this class so far. I didn't spell it right though. Let's try that one more time. Homomorphism if the idea is that it preserves the operation. So you really want to write it out this way. Let me not use A and B, let me use X and Y. So the idea is no matter what two guys you start with from A, you really want to write it this way. If I add them together in A, so what's the operation in A? It's not plus, it's box. So if I stick them together using the operation of A, and then I send that across, that should be the same as if I send them across individually, and then I stick them together using the operation in B. So the final equation that you get, if you don't say it in that way, it sort of loses some of that meaning, because the idea really is that you are operating in A, and then you send that over to B, versus you send each one over to B, then you operate in B. And because that's always the same, you're saying that the operation square and the operation star sort of behave the same. All right, so let's look at some more examples. Just from sort of easier to harder. So in this situation, we're going to use the integers and addition as the operation. And we're going to use that again for the second pairing. So this is my A square and my B star. I'm just going to use the same for both. There's nothing wrong with that, just to make the example easier. So I need an example. I need a function that goes from the first set to the second set. In this case, they're both z, both the integers. So here's what I'll define it to be. F of n equals 2m. So this is a homomorphism. So what this should do is preserve the addition in the first set when you send it over to the second set. So here's just a little mini proof of why this is a homomorphism. You have to let two guys be in, let me use a little different letters. So you don't have to use the same letters as in the definition. So you got to let two guys be in the first set. So in this case, they're both the same, but I'm really using this one. And then I just got to calculate these two things. So f of n plus m, so I can add them up over there and then send them over. Well, how do I send them over? Well, the function just says, take your number and multiply it by 2. So 2 times n plus m. So that's sending them over after adding them. But if I simplify this a little bit with the distributive property, well, isn't this just f of n? And this is just f of m. So it's true. So this is a homomorphism. Now, this is not the most interesting example because the two operations are the same operation. They're just addition. So what this is saying is, if you multiply by 2 and then add, it's the same as if you multiply both pieces by 2 and then add. But you're still in the end doing the same operation. So it's not really telling you. It's not very interesting. But it is good practice for how the proofs go. This is like the structure. Okay. So let's ramp it up a little bit here. Let's actually have two different operations, but this time we'll use the same set still. So this one's a nice example. So the real numbers, except we're only going to use the positive real numbers just for this situation. So don't worry about 0 or negatives, no 0. 0 is bad for this example. Okay, and then we're going to use the operation will just be multiplication times. And the other guy will still be the positive. It doesn't have to be positive, but I'll leave it as just a positive once again. And it'll be plus. So I'm going to find a function that turns multiplication into addition is the idea. So I need a function that goes from real numbers, the positive real numbers, to the positive real numbers. And it has to somehow turn the multiplication of two numbers into the addition of numbers. Well, you might remember a cool function called log or ln. And it actually does do this. So let's prove it. So I need to let two guys be an r plus positive real numbers. I'm not going to call them x and y because x looks like times. I'm going to call them, I'll just call them a and b or something. So then let's calculate these things. So over here, what's the operation I'm starting with? Well, it's sort of hidden. So I'm starting with multiplication and I'm going to addition. So that means my first operation before I send it over is multiplication, and I'm checking if I can send it over and then add, and that's the same thing. So really I should write, I'm showing this. And the way we go about showing it is really just calculating both sides, but you really can go from left to right or something like that. So we get this. So f of a times b, well, what does the function say to do? It just says log it, ln it. Now, why this works is you have to remember a log rule that says logs do this. So technically, this is like a whole nother proof on its own to figure out why this rule works. So you might not remember why this works, but I'll just let you say it. Okay. But that is exactly just f of a, and that's just f of b. So now I'm adding. So the point is I was able to turn multiplication into addition on the same set. So this function is a homomorphism. It turns one operation into the other. In a way that makes sense. So this is why, so homomorphisms are great. And I sort of want to just emphasize like what can go wrong. So the idea is in pictures, something like this. So if f is not a homomorphism, then the idea is something like this is happening between your two sets. And this is like bad, and you'll see why it's bad. Well, then what's happening is like, I can take my x and my y in here, and I can sort of stick them together. That turns into z, say for example. And my function says, well, because it's a function, it has to say where y should go. It has to say where x should go, and it has to say where z should go. So if I send x to A and y to B, and they don't combine into where z goes, then there's a misalignment. So let's just say, for example, that z ended up going to, I don't know, what's another letter? W. But A and B combined to be, using their operation, C. Well, now there's a mix up here, and it's because of that rule we're talking about up there. Because this is saying that if I combined x and y together, that should just be z. And then when I send z over, that should be w. But I'm also at the same time saying that, well, if I send x over, that should be a. If I send y over, that should be b. And when I stick a and b together with the operation over there, that should be c. But this doesn't work because I really want f of z to be c for things to match up. So that's the idea. When they do match up, that's a homomorphism. When they don't, then that's bad. That means your operation is not being preserved. Okay, so I just wanted to jump in just to remind you of what's bad before I do the next example, which is good because it's going to work. So this time we'll use addition first for the real numbers still, and multiplication second. And we're going to define a function that turns addition into multiplication. So we're going to go the other way. Let me use a different letter so I don't always have to use the same letter. So this function has to turn addition into multiplication. Well, how about this one? E to the A will do that. So I'm just going to speed up the proof a little bit. So G of A plus B means stick A plus B up there. And then if you remember your power rules, this is the same as that. So now we see where the multiplication comes into play. So now I've turned my addition into multiplication. Oh, except I changed the letter too. Whoops, these are G's. Okay, that's just one more example. Okay, so let's do a non-numbered example. So we need other types of examples too with no numbers in them. So here's a cool one. Let A be a set and consider the two things we've seen before. So the power set with the operation of union and the power set again, but with the operation of intersection. So just to remind you, the power set is the set consisting of all subsets of A. So it's got a bunch of subsets in it as its elements. And on the left, we're unioning them to combine two and to make a new one. And then on the right, we're intersecting them to do the same thing. But the idea is that these two things are sort of interchangeable. They just do the opposite thing, but they sort of obey the same rules. And we can show that by creating a function from one set to the other that preserves the operations. So what I have to do is I have to say where a subset goes, because those are the elements of the power set. So what am I going to send it to? Well, I'm actually going to send it to S complement, because the idea is that intersection and union are sort of two sides of the same coin. Whatever union does to one, the intersection will do that to the complement. So let's show that this actually happens. So the proof still works the same, even though there's no sets involved or anything, but it all works the same. So I need to have two elements of my domain of this function, which is the power set. So I need two elements of that. That means I need two subsets, of the power set. Sorry, elements of the power set. Get all mixed up. And what are these guys? Really, they're just subsets of A. That's what it means to be an element of the power set. And then I got to show that the homomorphism property happens. So I have to show that if I, so my first guy is union, my second guy is intersection. So if I union these two things, that should be the same as if I send them over separately and then I intersect that. So let's see that that happens. Okay, so first of all, this thing, what does it turn into under the function? Well, we complement whatever we plug in. That's what this function does. So I take this thing and I complement it. Now I have to remember De Morgan's laws, and this is the whole thing that works, that makes it work. Oh, those are just the result of plugging in S1 and plugging in S2, aren't they? Because what does the function do? It takes it to its complement. So that's just f of S1, that's just f of S2, but now I'm intersecting. So that's the whole proof. And so what this sort of does is sort of validate the idea of like unions and intersections are very much doing the same things in terms of like they just stick sets together and obey these rules that always seem to be the same rules that they both obey, and it's true. Okay. All right, so what else? So Okay, so homomorphisms are half the full concept that we're actually going for. But they are great on their own too. But this is even better. So when you have a homomorphism, but it's also bijective, it's even better. Then we say A is isomorphic to B. Now you remember this word, we used it before, but what we said was isomorphic as sets, and that was when it was just bijective and we weren't worrying about homomorphisms, but that's because with sets, you don't have an operation to worry about in the first place. So what this really means intuitively, this means that you can rename all elements of A in a one-to-one correspondence way while at the same time preserving the operation. So, and the other way to think about this is that A and B are really just exactly the same, except they have all their elements are named differently. Their operation is maybe named differently too, but they all interact the same. Once you rename them, the elements interact the same way as they do in B. So homomorphism, it doesn't have to be a bijective function on its own. So what that means is that the operations behave in a nice way. You can turn one into the other, but when you rename things, there might not be this perfect pairing that a bijective function gives you, but you can have overlap in a way that still works with the operations. Okay, so just to show you the example from the very beginning and how this fits into that. So if we use these two sets again, we can say that they are isomorphic with the proper operation. So this guy, we're using plus where we did 0 plus 0, 0 and that stuff. And then here we're using the operation where we did this. Oops. So not the arrow operation, but the first thing we did. So these two guys are isomorphic. Because of that function we created a long time ago. So if I just send 0 to true and I set 1 to false, it's a homomorphism and it's bijective. So they're isomorphic, but in this better sense, not just as sets, which is what happens when you don't have an operation and they have the same number of elements and you just do a renaming and you don't worry about operations. But if you do a renaming and there are operations, it's not necessarily true, as we've seen, that the operations will also work the same. And that was the point of this other example. So if I think about it, that other one, this, because of their cardinality being the same, being 2 means that they are isomorphic as sets, but when I attach the operation and I use this arrow operation, just because they're isomorphic as sets does not mean that they're isomorphic in this other sense. And that's because this thing did not or was not a homomorphism. Because the operation changed. So it's the same exact function. This is the same function as up here, but it doesn't turn plus into this arrow operation. So it's not a homomorphism. So even though they're isomorphic as sets because they have the same number of elements, they're not isomorphic in this other way. Okay, so one last interesting example of two things that are different, that are not isomorphic. So here's the set from last lecture that I sort of screwed up the operation, but I fixed it in the description, so go check that out. So this is the set that comes from all the symmetries of the equilateral triangle is the fanciest way to say it. And then here's a different set that also has 6 elements, which means that they are isomorphic as sets. So I guess I should name this, I'll call this B or something. So they have the same cardinality, so they're isomorphic as sets. But they really are different things because the operations are very different. So we talked about the operation on G last time. The operation on B is going to be this congruency stuff. But if you don't want to make it hard on yourself because you don't remember that stuff very well, just think about it as adding on a clock with 6 numbers. So for example, 5 plus 3 is 8, but on a clock with 6 numbers, that wraps back around, because it starts at 0, it wraps back around to 2. So that's the operation on B. And they really are different operations, but it's kind of hard to show that they're not isomorphic, because the definition of isomorphic means that there does not exist a function, which is homomorphism and bijective. And if you want to show there doesn't exist something, it's kind of hard, because what are you going to do? Run through every possible function and see that none of them work? That's kind of hard. But there are simpler ways to see that they're not the same, besides trying every possible function. So there's simpler ways to see that these are not the same. They're not secretly the same 6 elements renamed, and their operations are actually the same, just everything's been renamed. They're actually different. That's the whole point. So what people in math do is they come up with a new concept, like a set together with an operation, and then they say, like, what are all the possible ones you could ever think of? Because are these two really any different from each other? If they're not different, then if they're not different in this renaming sense, then they're not really different. You think of them as the same. And so we want to know if they're actually different. So here's one little, just quick check you could do to see that the operations actually differ. So for example, if I flip over A and I flip over A again, that just takes me back to nothing, which was R360. It was the nothing element. If I flip over B and I flip over B again, then that's also doing nothing. And if I flip over C and then I flip back again over C, that's also doing nothing. So we have these very strange properties going on in this set where we have these three elements that if I combine them with themselves, it's the same as doing nothing. And then you can look over here and you can see that there's nothing like that over here. So 0 is the identity element. So they both do have an identity element. This guy was the identity element. Does nothing. They both do have one, but the one on the left has this weird property that the one on the right does not, because on the right, the only one that has that is 3. 3 plus 3 equals 6, which is 0. Oh, sorry, I added too many numbers. There should be 6 total, so this should stop at 5. So they have 6 elements. That one had 7 before, I screwed it all up. Okay, now they both have 6 elements, and 0 plus 0 is 6, which is, sorry, 3 plus 3 is 6, which is 0 on a clock. Okay, so, but there's no other number that does that in this set. And so for the two operations to secretly be the same but renamed, you would need f sub a would have to go to 3 in order for, so you would need a function that does this. Let me write it properly, sorry. You would need a function that sends that to 3 because you would want this to happen. And this would be the only way that could happen. So FA box FA, that turns into doing nothing, rotating by 360. And on the right, FA is 3 plus 3 is 0, so you'd want this to go to 0. But then at the same time, you would also want f of b to do the same thing, but why doesn't this work? Well, because now it's not a function, because you have two different, oh wait, sorry, that's fine. It's still a function, so I could do that, but now it's not going to be bijective. Because I'm sending two things to the same place. But I have to do that if I want this property to hold for f of for flipping over b as well. So we're stuck. There's just no way around it. If you wanted to obey this homomorphism property where the two operations are compatible, we can turn one to the other in a consistent way, then you have to send two different guys to 3 to make that work, because 3 is the only element obeying this weird property that when you add them up, it goes back to doing nothing. But over here, you have 3 different ones that do that. So they all got to get sent to 3. Okay, so in any case, that's the end. The whole point is that people study sets with operations. And if you want to know when 2 are the same, you have to create a function that turns one operation into the other. That's bijective. Okay, so see you later.